Okay, thanks a lot for the introduction. So my name is Juraj, and this is a joint work with my colleagues Denis Kupsa, Christian Mainka, and Jörg Schwenk. And actually, this is a paper which was published in the summer at the workshop of offensive technologies. So I am a security researcher, actually, at the Ruhr University of Bochum, and the chair for network and data security. Which is hosted by Professor Schwenk, and we are doing research on web services, single sign-on systems, applied cryptography, SLTLS or cryptocurrencies. We are doing provable security and attacks and defenses. And we are a part of Horst Goerz Institute for IT Security, and there are further topics like embedded security, crypto, malware, and so on. And we are also doing penetration tests and security analysis and so on in workshops. Okay, so today I'm going to present you our recent work on how to break XML encryption. So first, I'm going to present you what is a web service and XML security, because I'm going to explain how to apply the attacks on XML encryption in the area of web services. Then I'm going to present you some basic background on XML signature wrapping and attacks on XML encryption. These attacks are a bit older, but they are relevant for understanding the basic problems in automatically adopting XML encryption attacks. Then I will give you an example of a concrete attack on XML encryption, on the symmetric encryption scheme, and then I will discuss countermeasures and problems. Maybe it gets a bit boring, but don't go away, because at the end I will show you a demo of our WS attacker tool, which allows you to decrypt XML ciphertexts. Okay, so let's start with web services. So what is a web service? In this case, we are handling SOAP-based web services. So SOAP web service is a standard which allows you to execute remote procedure calls. So imagine we have a server which generates some prime numbers. And we have a small client who wants to grab some prime number, so he wants to execute the function getPrime on the server. So what he does, he sends a function call to the server, and this function call has to be wrapped in some message structure. So he wraps it into the envelope, body, getPrime, and sends it to the server. The server generates some prime, and this prime is then sent back to the client. Okay, and this is again wrapped into the envelope body and the prime element. This is the basic idea behind remote procedure calls and behind web services. So this was a very, very simple scenario, but we have many complicated scenarios, like where we have some brokers. So for example, imagine we have a client who wants to communicate over his broker, and he wants to have some insurance reservation or flight reservation, and he wants to pay it in his bank, and he does everything over his broker. So this is a complicated scenario. This can be also achieved using SOAP-based web services automatically. So what is the problem? So what happens if we now want to use security? Many of researchers would tell me, okay, we can use SLTLS to secure these connections. And what is the problem of SLTLS? So if we apply SLTLS on this scenario, then only the connections between the client and broker and between broker and bank is secured. So what does it mean? So if this client generates a message and sends it over the broker to the bank or insurance company, then the message is secured only during the transport. This means the broker can see the data. Maybe there are some confidential credit card numbers or something like this, yeah? And we don't want to reveal this data. So what do we need? We need something what's called message level security. So we need to apply some kind of lock on the message directly, send it over the wire so that the broker cannot decrypt it, cannot modify it, and at the end only bank or insurance company can decrypt this data. Okay, this can be achieved using XML security. So XML security describes methods for applying cryptographic algorithms to XML. And it basically consists of two standards. It is XML Signature and XML Encryption. XML Signature protects authenticity and integrity of the data, and XML Encryption protects confidentiality. So it is very flexible. It allows us to secure the whole document or specific elements or element contents or more elements at once. So you can encrypt or sign specific elements. And so many of the researchers I'm talking to are asking where is it used. So it is not that used in the browsers or in these technologies which are visible to us, but it is used in the backends of large industry companies, for example, in the banking standards or single sign-on systems, and so on and so on. So it is quite frequently used. Okay, so what is the problem of XML security, so of this XML signature and XML encryption? The first problem is called XML signature wrapping. What can we do with it? So first, what is XML signature? So XML signature allows us to secure the message, the authenticity and integrity of the message. So how can we do this? So imagine we have this envelope structure with a header, and we have this function invocation called monitor instances. What we do is we first create maybe some timestamp to ensure the message is always fresh. And then we create a signature, and we reference first the body element and the timestamp element using this URI or ID-based referencing. Yeah? And then we compute a digits value over these elements and compute a signature over the whole signed info. So this way we achieve that using this URI referencing, these two elements are secured. Yeah? What can go wrong? So there's a problem called XML signature wrapping. It is very simple to describe. So imagine we have an attacker who eavesdrop or get in possession of this message, and what he can do. So we have this signed body element, and what he does, he creates a wrapper element somewhere in the header. He moves the original body element, the original structure, to this wrapper element. And this ensures that the URI now references, or the signature, the reference references this element in the wrapper. Okay? And there is now place for the next body element, so he can now modify the body element and include arbitrary function. This is called XML signature wrapping and was actually already described in 2005 by two independent groups, by McIntosh and Austell and Bhargavan et al. So it's very simple, looks to be very simple. So what is the problem? So why does the attack work? Maybe you ask. This is very simple. So the most of the cases, the web service verification and business logic work in two steps. So there is the first verification logic, which contains signature validation and cryptographic functionality. This is very, very complicated. So most of the developers apply some cryptographic library. In the second step, there is this application logic, which just invokes a functionality. This is done by a developer on his own. So what it does then, on the end, the verification logic goes to the envelope, header, security, signature, reference signed info, finds the URI body and validates it. Okay, everything's correct, everything's validated. The application logic now goes to the envelope body and executes the function in the body element. So this is the problem in signature wrapping. You could mean this problem is very simple to overcome and to deploy some countermeasures, but there are many attacks in the recent years that were published. So the recent one is maybe okay. So there was a problem in XML signature wrapping in Amazon interfaces. So there we showed in 2011 in our paper "All Your Clouds Are Belong to Us" that the attacker can invoke arbitrary functionality on the Amazon cloud. So there was a possibility, like the client could invoke SOAP invocation calls using signed SOAP messages, and for example, start new instances on the cloud, and so on and so on. And it was possible to execute signature wrapping. So what the attacker could do, he could eavesdrop the message, modify it, send it to the cloud controller, and maybe start new instances, create new instances, get private keys from the server, and so on and so on. So he could get the whole cloud of the customer. Okay, so this was in 2011. Last year, my colleagues published a nice study on SAML-based attacks. So this is a single sign-on protocol, which allows you to log in on specific services. And my colleagues analyzed software as a service applications, on concretely 22 software applications. They analyze, for example, attacks. Maybe you are familiar with XML external entity attacks. They analyzed that there were 10 out of 22 providers were vulnerable to these attacks. And they also analyzed XML signature wrapping attacks, and 1/2 of these software as a service providers were vulnerable to these attacks. So it was possible to log in as an arbitrary user at these providers. So if you work with SAML, I encourage you to read this paper. Okay, so let's start with the attacks on XML encryption. I will just give you a basic explanation first, how the attacks work, and the scenario, and then I will go to the concrete description of a specific attack. Okay, so in most of the cases, we use hybrid encryption scheme in XML encryption. What does it mean? So imagine we have this envelope and body element, and we now want to encrypt the content of the body element because there's some confidential data. So what we can do, we create first the encrypted key element and the encrypted data element. And then in the encrypted key element, we use some public key encryption algorithm to encrypt some symmetric key. Yeah. So first we use RSA maybe to encrypt some symmetric key, and in the encrypted data, then we use some symmetric key algorithm to encrypt the data. For example, you are maybe familiar AES. Yeah. Okay. And then we bind these two elements using some data reference. This is how it is done in XML encryption. The problem is, in 2012, we published attacks on XML encryption on the asymmetric part using so-called Blankenbacher's attack. It was on this encrypted key. And then back in 2011, we published attacks on the symmetric part, and how to decrypt the data directly in the which was symmetrically encrypted. And both of the attacks are adaptive chosen ciphertext attacks. What does it mean? So what is adaptive chosen ciphertext attack? So imagine we have a client and a server, and the client sends some confidential data, some ciphertext to the server. This is just a basic scenario. How does the attack work? Or both of the attacks. And we have an attacker who eavesdrops this ciphertext, or maybe finds the ciphertext with confidential data. He uses the web service as an oracle, modifies the ciphertext, sends it to the oracle, and the server responds with valid or invalid. And he repeats this several times with different modified ciphertexts, and at the end, he can decrypt the message. Okay, this is the basic scenario behind adaptive chosen ciphertext attacks. And as already mentioned, we described attacks on the asymmetric part using Blankenbacher's attack, and on the symmetric part. And in the symmetric case, we could decrypt one plaintext byte using 14 queries to the server, using 14 Oracle queries. And in the asymmetric part, we needed about 400,000 queries to a few millions of queries, but we could decrypt the whole symmetric key. Okay, good. So in the next few slides, I will show you the basic idea behind this attack on symmetric encryption. So how does it work? It will be a bit math, but don't worry, it's okay. Okay. So we start with the attack scenario, and so we have, as already mentioned, this adaptive chosen ciphertext attack. So we have an XML encryption ciphertext, and the attacker sends several ciphertexts to the web service, modifies them, and at the end he can decrypt them. So maybe you ask now several questions. So in the next few slides, I will show you what is a valid ciphertext and why we can use a web service as ciphertext validity oracle, and how to use it to decrypt a ciphertext. Okay. Good. So plaintext validity. So XML is a text-based data format. So this means that every before we can execute some business logic or evaluate some data, we have always do some XML parsing, you know it. And the characters that are included in the XML are usually encoded using some standard, and they are usually encoded in ASCII. You probably, everybody of you probably heard about ASCII. So ASCII is a standard which consists of 128 characters or symbols. And this ASCII table contains some specific symbols. So for example, the 00 character is the null character or null byte. Then we have some specific symbols like 07 is the bell character. And then we have some specific symbols like escape, yeah? This is on the left column. You don't have to understand or see everything, but we have here some specific symbols on the left. These symbols are not parsable. Yeah? Okay. Okay, so what we need to know for the next few slides, what you need to remember is that these in the left column are not parsable. We say they are not type A character. Then we have here also some specific characters like ampersand or left parenthesis. This is also not parsable or type A characters. And then we have here some specific characters like horizontal tab, line feed, or carriage return. These are type B characters. Also, we have here some specific characters from the alphabet. Okay, and in the next few minutes, we will consider that valid plaintext contains only type B characters, so these parsable characters. Why can we use a web service for plaintext validation? So imagine we have a web service which accepts some ciphertext. What does it need to do? So it proceeds in these three steps. So first, it needs to decrypt the content. Then the content has to be parsed, and then there's some business logic evaluation. So, and there's a problem every time this should happen. So there's always this XML parsing. And if XML parsing fails, so if there's an invalid plaintext decrypted, then we get a parsing error, and maybe the server responds with some fault message. Yes, so if we send an invalid character from the ASCII table, which is decrypted, then the server responds with a fault. Good. So to give you a basic idea behind that, just consider this ASCII table and consider how the data is decoded. So imagine we have these 128 characters, and we always encode ASCII characters in 1 byte. So a byte consists of 8 bits. So the first, or the 0 bit is always 0, because we have only 128 characters. The bits 1 and 2 show us in which column we are, yeah? And bits 3 to 7 say in which row we are exactly, if we encode it, okay. So ASCII exhibits a nice pattern of type A and B characters, as we could see, so this valid and invalid. And now for a short time, I will describe later why this is possible. Suppose we can flip arbitrary plaintext bits, and we can use it and we can use this plaintext validity oracle. So let me give you an example. So we have eavesdropped a ciphertext, which contains some cipher encrypted black hat, and we want to decrypt or determine bits 1 and 2 of the first character. So we want to find out bits 1 and 2 of the character B. So we do not know as an attacker that there is a B included, but we want to decrypt it, these 2 bits. So we are here on this position, so in this column, in this third column. And now I can ask you, so what happens if the attacker now can flip a bit and he flips bit 2? What happens? Okay. Yeah, so if we flip bit 2, exactly, then we move to the right, because we flip bit 2. If we flip now bit 1, we jump to this column, And if we flip bit 2 again, we jump to this column. And if we send this 4 ciphertext to the server, then once he responds with an invalid message, with a fault message, because there is an invalid character. So at the end, we know. So if we flip bit 1, then we jumped here. So we know the original column was this one. Okay. So this was the basic idea behind this attack. And further, we can proceed with further rows. So we can flip some bits in bit 3 to 7, and we can go there and decrypt the whole plaintext byte. And okay. Now, why is the bit flipping possible? This is because of AES-CBC cipher block chaining mode of operation. So imagine we have a cipher block chaining mode of operation. So we have an initialization vector. This is how decryption works. And the ciphertext block, the ciphertext block goes to the AES function, and the initialization vector goes directly to the XOR function. So if we flip a bit in the initialization vector, this goes directly to the XOR function, and we flip also a bit in the plaintext. This is why we can flip bits in plaintext. This was actually misused in several attacks, like padding oracle attacks. Maybe you are familiar with them. They were applied to several encryption schemes. Okay, so we improved the attacks a bit using these character tables and so on and so on. You will see the performance in the live demo. But what exactly? So you can see with the number of the encrypted blocks or bytes, the number of server records just goes up linearly. And we need about 14 queries a plaintext byte. Okay, so this is quite performant. So we need to apply some countermeasures. And this is what we analyzed in the recent research. So how can we apply countermeasures, and what are the problems in the current applications? So the basic idea behind applying a countermeasure is to protect the integrity and authenticity of the ciphertexts. Yeah. So, but it's not that easy as I presented in the first slides. So what are the problems for this? So the first problem is signature wrapping. So imagine we have an encrypted data here, an encrypted key, and this encrypted data should be protected using a signature. What can an attacker do? He can just move the signed data here, and the signature is still valid. And he can place arbitrary encrypted data to the body element. It gets decrypted, and you get an oracle. Okay, this is the problem, the first problem. The second problem, so in this case, the signature validation always works, and there is a decryption of functionality which can also work, or if there is an invalid character, the server responds with a failure. Then there is a problem called XML encryption wrapping. So imagine we have, again, this function. What the attacker can do, he can just define an additional encrypted data and cipher data or encrypted data element. And the server not only processes this or decrypts this body element, but also in addition this one. This is, for example, the standard configuration by IBM Datapower if you work with them. Yeah? So if you define an additional element, the signature is validated because, okay, the body is the same. This body element also gets decrypted and the business logic gets executed, but here maybe there is a problem with the decryption. Okay. So now there is a question how to analyze this automatically. So we saw there are different problems, like we have two adaptive chosen ciphertext attack. This is attack on asymmetric encryption scheme. On the symmetric encryption scheme, we can combine it with XML signature wrapping attacks or XML encryption wrapping attacks with several countermeasures. So how can we analyze them automatically? And this is why we created a tool or a new plugin for our WS attacker. So WS attacker is an automatic penetration test tool for web services. If you want to download it or play with it, its sources are available at GitHub, and it supports many attacks. And there's also a new plugin for XML encryption. So the basic approach behind attacking XML encryption is to analyze the message security. So what what XML security mechanisms are there? Is there XML encryption, signature, and so on? Can we attack it? Can we remove XML signature protection if it is there? And at the end, we have to apply the attack. Okay, so we have these three phases. So the first one is the detection phase. So imagine we just received XML security message. Then we have an avoid phase and we have an attack phase. So imagine we have received an encrypted XML element. And now we have to identify the XML security mechanisms. This is an offline phase, so we have maybe this message, and this message consists of some encrypted key, some signature elements, and so on, and we need to know what is protected. So in this case, we know that encrypted key is bound to the encrypted data element, so we have here some XML encryption. Then we have here signature over the body element, and we have here some timestamp, some additional timestamp mechanism. So this is what we need to analyze first. Then this analysis is going to the knowledge pool, and we proceed to the next phase, to the avoid phase. So we need to somehow execute the attacks, and if the message is expired, we need to execute signature wrapping attack to make it, to make the attack working again, to make the web service accept the message. So maybe we can execute some, there's an XML signature. So maybe we can execute some XML signature wrapping attack on it. I presented already some XML. I presented already some XML signature wrapping attacks, but with simple XML signature wrapping. But there are more problems which can come. So there may be there are different positions where we can place the signed element. There are different IDs which can be used, so XML signature can get complicated. So we need to do this automatically. Then if this works, so if we can overcome the XML the timestamp using XML signature wrapping, we can proceed to the signed encrypted element. So what we need to know, so if there is no signature of the encrypted element, we can proceed to the further step. If there is a signature of the encrypted element, we can again execute XML signature wrapping. Or if this works, then we can go further. Or if this does not work, then we can execute XML encryption wrapping. There are several steps. And at the end, if we could overcome these protections, we can send several requests to the Oracle and map them to the valid or invalid ciphertexts. This has to be done. So what we need to do, so we have some chosen ciphertexts, some XML encryption ciphertexts. We send them to the server, and the server responds with maybe some stack traces, maybe with some invalid messages, but we do not know what's valid or invalid ciphertext. So we need to map them to valid or invalid and construct our Oracle. So this depends on the implementations, because there are different servers, different application firewalls, which use different approaches for this. And at the end, if we could identify the Oracle, we can execute the attack and decrypt the message. So we analyzed 5 servers and application firewalls. So we analyzed Apache Axis 2, Apache CXF, XML Gateway, IBM Datapower, and Microsoft Windows Web Services implementation. And we found out that the asymmetric attack is in the default case applicable to Apache CXF and XML Gateway, and the symmetric attack is applied as applicable to Apache CXF and access to XML and also IBM Datapower. There are different countermeasures which are applicable, but you have to really take care how to apply them. So I will present you later some problems with them and how this worked. Now I will present you the WS attacker framework. Okay, so what I have here now is an Apache Axis 2 web service which is running and which accepts some messages on this port on the local host, and we can see that there is a WSDL, which is with the description language of the web service. This is not what we need to take care about. What we now assume, we have eavesdrop a SOAP message. So what you can see here now, there's it looks a bit complicated, but there's an XML signature, and this XML signature references some elements using the reference element, and we can see that there's encrypted key, and we have also a timestamp, so the message is protected. The timestamp is signed, it is protected, and we have also a signature over the body element where the encrypted data is. So it's very complicated to execute the attacks. How can we do this? Okay. So this is our WS attacker framework. So what it consists of several phases. So in the first phase, we need to just load this description of the web service. This is this WSDL file, and we can define some bindings. We are now, the message was in the SOAP 1.1 binding. This is not necessary to know, but this is how we initialize the WS attacker with the server configuration. Now we know that we eavesdrop this SOAP message. So we take the original SOAP message that we eavesdropped and we paste it for the initialization to WS attacker. Yeah? And send it to the server. What happens is, okay, there is some failure. I don't know if you can see this, but there is the message is expired. So we have a timestamp protection. So okay, that's not that good, but maybe we can overcome this. So what? Okay. So now we have initialized WS attacker, and we want to execute the attack. We have a choice. We can choose between several attacks which are defined in the plugins. So we have here also some denial of service attacks if you want to work with web services. We have spoofing attacks for sub-action WS addressing spoofing, and we have also attacks on XML encryption and XML signature. If you work with web services, you can apply them directly. Today, so I'm going to present you this XML encryption attack. So how can we proceed to adapt them? So, okay, so we can see in the configuration that WS attacker already mentioned that there's some encrypted key, and found out that there are these two elements. So there's XML encrypted key element and encrypted data element. What we want to do now is to execute the attacks maybe on the symmetric part, so on the CBC attack. So we can execute also PKC as one. I will present you the CBC attack, and we can choose whether we want to execute signature wrapping or encryption wrapping attack. We choose for now signature wrapping, and now I have to configure a threshold. Okay, this is for the configuration of the oracle. Now we have here encrypted key and encrypted data element. We want to attack, so it's CBC ciphertext, so this is the symmetric part, so we want to attack the encrypted data element. And at the end, we want to configure this oracle. So we want to modify ciphertext to the server and observe their responses and map them to the valid or invalid requests. So we send several ciphertexts to the server, and these are sent on behind. And at the end, we receive two messages. And as we can see, so there is a message which contains some bad padding exception maybe, and so on. This is probably an invalid message. So we set as an invalid. And there we get a message which contains some validly encrypted ciphertext. So maybe this is a valid message. So we say this will be valid message, this will be invalid message, and this is what we need to do. So what we do now, we just start the attack. And in the attack, we can see this is how it proceeds. So we can see how the bytes, the requests are sent to the server, and every like 14 queries we can decrypt a byte. This is how it works. And at the end, okay, the ciphertext is not that long, so at the end we can see maybe the decrypted ciphertext. Okay, so there we go. There's an decrypted ciphertext, and we can see there was a dummy message with "Hello World," which was currently decrypted. Yeah, so we decrypted about about 200 bytes with 4,000 server queries. So this is quite practical. And we also find signature wrapping position to execute the time to overcome the time stamp protection. If you want to play with it, the recent version of WS Attacker also allows you to configure a server proxy. So you can run it through burp or zap proxy and to see the messages that are generated. But yeah, this is what you need to know about WS Attacker for now. Okay. So if you have any questions about WS Attacker, you can come to me later. So now we can proceed with the two more minutes. 3. Okay. Okay. Okay, so you can see I have also some backup slides if something would go wrong, but I was lucky. So there were also some problems. Maybe I can go at 2 more slides about the problems in Apache CXF. So basically what we have in our decryption processing, we have 2 steps, as already mentioned. There's a hybrid encryption scheme. So we first use asymmetric encryption to decrypt the symmetric key K, and then we use symmetric encryption like ASCBC using the cipher data. Okay, and we found two bugs in Apache CXF by the message processing. So first, there was a signature protection which you could enforce using a specific parameter required signed encrypted elements to true. This enforced the data was every time verified. The signature was always verified over the encrypted data before it was decrypted. But what we could do, we could apply a signature wrapping attack to this. So this was the first bug in Apache CXF. This was how we could apply this the attacks on the cipher blockchain mode of operation. There was also a problem in the asymmetric part. So if the asymmetric ciphertext gets invalidated, then there is no symmetric decryption possible. So this could lead to a specific side channel. So the server cannot decrypt the CBC ciphertext, so it responds with a different message. So how can you protect it? You can, if it gets good, if the decryption is correct, we proceed with the key K. Otherwise, we just generate random 128 bits, maybe for this ASCBC. Yeah, so for the ASCBC, we need to generate random bits, and then we proceed with the decryption. But what the Apache CXF did was it generated 128 bytes instead of 128 bits, and then was a different message generated, and we could also apply these attacks on these Blankenbacher attacks on the encrypted key part. So this was an invalid countermeasure, so the developer knew about the countermeasure but applied it differently or invalidly. I don't want to blame him, but I just wanted to point out that this is very complicated to get it working correctly. Okay, so if you want to play with it, so go to the GitHub, there's our WS Attacker. If you want to play with some web services, I encourage you to use Apache Axis 2, because it is vulnerable to most of the attacks that WS Attacker can provide. So this is quite nice. And if you want to have some examples on configuration of Apache Access 2 and how to get it running, go to our blog post. Okay. So in conclusion, if you want to use some countermeasures, please do not use AES CBC or PKCS 1.5. They are insecure. XML encryption got updated to AES GCM. Not all of the servers support it, but so if you can, then use RSA OAP or AES GCM. If you have to use AES GCM or ASA PKCS 1.5, ensure that you can first validate the XML signature over the ciphertext, and that the attacker cannot modify the ciphertext and to get an oracle. So, for example, in IBM Datapower, you can select specific elements which are going to be decrypted, then you can sign them, and every time ensure that only specific elements are encrypted. Okay, to conclude, so XML is very complex, especially XML security, because it combines some XML standards, XML security standards, cryptographic mechanisms, and so on and so on. So if you want to apply XML encryption or XML signature, then please use WS Attacker for evaluation purposes. And if you are a researcher, maybe, then take a look at different standards, because these attacks are applicable also to standards like XML, JSON web encryption, and so on, or WebCrypt API maybe. So take a look at it. And if you are a developer who is deploying secure systems, please consider to apply secure standards like AES GCM or CBC. Okay, so this was it. Thank you.
Thank you. We've got time for one more question.
You mentioned in your slides, I think that Microsoft Web Services are not affected by this. Why is that? Is that because they use GCM or protocols?
Yeah, so Microsoft was a web service framework which allows you to deploy these web services, and it is not a firewall which handles the messages like in an arbitrary way, in general way. So what they did, they provided only 3 implementation or configuration steps. Either you can omit XML security, or you can use XML signature, or you can use XML signature and XML encryption. And the positions of the elements were fixed. So they strictly validated whether there is only one encrypted data element and the position of the element, and whether it is signed or not. And we were not able to proceed further with different messages, because every new message with new generated encrypted data key or encrypted key was just rejected. Okay. And this is the problem in firewalls like IBM Datapower or X-Way. They have to be configured like in a general way, and the problem can happen. So if you configure it in a general way, then maybe you can ensure there are new elements coming, and so on and so on. But Microsoft was a good example of how to do it correctly.
Thank you.
Thank you very much.
Okay, thank you.